Hi, I'd like to do 3 limits at infinity with you, and we're going to work on limits of rational functions today. So let's do a first one. I would like to explore with you, please, the limit as x approaches infinity of 9x squared minus 2 over 6 minus 20, nope. Yep, 6 minus 29x. Yep, I can write. What we're going to do is we're going to explore what happens to the values of this function as x goes to infinity. So x is getting bigger and bigger and bigger. In terms of a picture, I've got some axes, and x lives on that axis, and then function values live on this axis. And as we feed values from along here through this function, it returns to us a number, and that number is the height of my function across the x-axis. And we just want to see, like, well, what does the height turn into as we go that way forever? Is it going to get bigger and bigger and bigger? Is it going to go down into the ground over there and go toward minus infinity? Does it approach some value as x gets bigger and bigger and bigger? So I'd like to do this one algebraically with you. And we'll do that by looking at the leading behavior using a theorem in calculus that says that for rational functions, so this is a rational function. So this is a ratio of two polynomial flavored functions. So essentially, we have something polynomial-like. And when we divide those in this ratio, right, we have one on top and one on the bottom, we get a rational function. So we have a rational function. Yep, that's totally off screen. I'm going to leave it. It'll be okay. With polynomials, as x gets bigger and bigger and bigger, one term will dominate all of the other ones. Compared to one term, every other term is going to be small, insignificant, and ignorable. So our mission in doing these kinds of functions right here, the trick in our algebraic drawer of tools that we're going to use to work this thing out, what its actual value is going to be to explore the leading terms. Why do I not just get a substitute? Well, x is getting bigger and bigger and bigger, and this thing is infinity, which is not a number. So I can't, formally speaking, just plug it in and evaluate. I have to do some other tricks to figure out what the precise value of this thing is. Over time, you will develop habits that let you look at something like this and just be like, oh, I know what it is. And so part of this is you doing enough of these problems that you build up experience to be able to do that, right? So it's just like swatting a ball, which I'm terrible at, and I'm sure my form, if you're looking at my form, that's probably what I really do if I were to try to bat. So there's a reason that I don't do that. I could get better with time, and it's hard. Okay, so let's look at the leading terms of the numerator and denominator of this function. Which ones are going to get the biggest as x gets bigger and bigger and bigger? The numerator, you can't see that marker. The numerator is 9x squared minus 2. That's the stuff in top. And as x gets bigger and bigger and bigger, this part's going to stay the same. The 9x squared is going to stay the same. But this 2, 9x squared is going to vary. This 2 is going to get, is going nowhere, right? X can change all at once. This 2 is going nowhere. So we can safely ignore this term near infinity. And this term is going to dominate. So we have our 9x squared minus 9x squared is our leading term. Now we just need to do that on the bottom. The 6 is fixed. Change x all you want. 6 is going nowhere. The 29x is totally changing. And I'm going to be sure and include its SIG and sign as I indicate that it's the leading term. So the theorem for rational functions at infinity says that we can just ignore everything except for these two terms. So I'm going to write a line here. And then I want to come back and talk a little bit about it. So this limit is equal to the following limit. The limit as x approaches infinity of 9x squared divided by negative 29x. What I'm not saying is that this function as an entire entity is the same as this function as an entity. I'm not claiming that. I'm claiming that their limits are the same. That if you were to look at the picture for this one and the picture for this one, and you should do that. You should plot this function. You should plot this function on your calculator, and you should see that near infinity, out there toward the right-hand side of your screen, these two things tend toward the same value. Nowhere do they take on the same value, except for a finite number of points. But toward infinity, they move toward the same thing. So I only have to consider those things. And in fact, using that same theorem, I can actually write 9 over minus 29 times the limit as x approaches infinity. And I only have to look at the powers in these two things right here. So I got to put an x. The top number is going to go right here. I'm going to subtract the bottom number. There's a hidden 1. I like to just not write ones because it makes things look pretty tidy. So 2 minus 1. But what's 2 minus 1? It's just our friend 1. And this thing gets bigger and bigger and bigger as x goes to infinity. So this value ends up not mattering in this case. And this limit is equal to infinity. More space on this one. Let's try the limit as x goes to negative infinity this time. So we're going to go to the left of 2x to the 5th plus 3x to the 4th minus 31x divided by 8x to the 4th minus 31x squared plus 12. Okay, so we're going that way. We've got a numerator and a denominator. Substitutions, a tactic you can use with this. It's not formally that well defined, although one can use it with intuition to help figure out what some values are. I'm not going to do that right now. Instead, I'm going to use the theorem that says that we only have to look at leading behavior for limits of rational functions. So once again, imagine we're just presented with this function from the first time, for the first time. You didn't know that we were going to be looking at this particular function. It'd be like, well, what do we know about this function that means that I can use techniques and tools on it, recognizing that it's a rational function, that it's a ratio of two polynomial-like functions, is part of the key to solving this problem. So recognizing which tool to use is just as important as using the tool correctly. So we will rarely actually tell you what tool you need to use when doing a limit. That's part of the skill also. So we're just going to look at leading behavior for this function out near negative infinity. Way over there. So out near negative infinity, the terms with the highest power are going to dominate all of the other ones. They're going to overwhelm all of the other ones. So compared to x to the 5th, x to the 4th, and 31x, they're not doing squat. So, so we're going to go ahead and say, well, you might as well not be here. You might as well not be here. Near infinity, those things won't matter compared to this term right here, the 2x to the 5th, because this one's the biggest. That power up there is the biggest. That's the biggest power. That's the biggest power. And then similarly down here, I've got that. So the theorem says that I changed colors. That wasn't what I intended. I'm going to leave it. That this thing is equal to the limit as x approaches negative infinity of 2x to the 5th over 8x to the 4th. Now I'm going to work on canceling stuff out here. That's equal to, I'm going to pull this 2/8 out front. I'm going to take a 2 out of each of the 2 and the 8 and bring that up front into a quarter of, now I'm dividing 2 x's right here, and so I'm going to subtract the lower one from the upper one. And it's going to turn into x, well, the limit as x approaches negative infinity of x. And now be careful. That little minus sign right there, make sure that you pay attention to it. So when this number right here is odd, and check it, so that power right there is odd, so we have to pay special attention to what's going on at the negative right there. So when we plug a negative infinity, we've got an odd number of negatives going on, and that number is simply equal to negative infinity. I'm pretty proud of my negative sign. Not my negative signs. Well, I mean, those are pretty easy to do. I was going to say I'm pretty proud of my infinity signs. I've been working on those for quite a while now. That one's really good. This one is pretty... It is what it is. All right, let's do one more before we call it on this video, okay? So let's take the limit as x goes to infinity of square root of 36 x squared plus 7 over 9x plus 4. There's a theme. There's a theme in these problems. The theme is rational function, behavior out near positive or negative infinity. So I'm going to kind of just like dive right in on this one. Hopefully you're into it. The first thing we're going to do is consider the leading behavior of this thing. So I'm going to consider the stuff underneath the square root first and recognize that the square root happens after that. So make the observation, my friends, that if I put in some really big number for x, then this square is going to be even bigger. And this 7, I might as well not be adding it. 7 is a drop in the bucket compared to any flavor of infinity. So I can safely ignore the 7. The leading behavior of the stuff underneath the square root sign is that 36x squared right there. So we're going to focus our attention on that. Similarly, in the bottom, the x term is going to dominate. The 9x term right there is going to dominate. So I'm going to rewrite that this is equal to the limit as x approaches infinity of the square root of 36x squared divided by 9x. I'd like to emphasize once again, I'm not saying this function equals this function. I'm saying the limits are equal to each other. If I didn't have the limit sign out front of this thing, the thing that's saying, hey, we're considering moving values of x and seeing what happens as it moves further to the right, I wouldn't be able to write these two things. These two objects, this function and this function, not equal to each other. They're not. So let's apply our square root now. And we'll write that that is equal to the limit, excuse me, as x approaches infinity, square root of 36. I remember that one because I remember squares, like 1, 4, 9, 16, 25, 36. So it's 6. Square root of x squared is the same thing as the absolute value of x, but x is positive. How do I know that? Well, it's going toward positive infinity, so I'm just going to ignore the negative numbers, which means that the absolute value of x is x. I do not know where the squeaking is coming from, but we'll deal with it. Okay, so I'm just going to write times x right there, divided by 9x. My x's cancel, and I'm left over with the value 2/3. 2/3. I would like to encourage you to go ahead and check your work when doing a problem like this. So let's make sure that I did it correctly. I've got my TI here. My TI. So I'm gonna go into the y equals. That's my top button. I'm gonna go to y equals and I'm gonna enter this function into it. So I'm gonna be all like square root of 36x squared plus 7 divided by, don't forget to use parentheses on this action, 9x plus 4. These parentheses are going to be your friends. So I'm going to graph it. So it should be going to 2/3. So I've got the thing on trace mode. That's on my TI-84 here. I've got it's my like F4 calc trace button in the top row. So I'm pushing the trace button, and then I can just move I get a cursor, and I can just move it to the right. And it totally looks like this. Yeah, absolutely. It's like 0.64, 0.645. I'm at like 0.65 now. And if I keep moving further and further to the right, it's going to take a while. But this thing's, I mean, numerical evidence right here, strong numerical evidence, this thing is moving toward 2/3. Another thing you could do is you could plug in like a big number, say like 1,000,000, seems pretty reasonable. Maybe 1,000 would be good enough. Plug in 1,000 each for these things, and you should get about that value. So you should be able to estimate what that value is to check your work. Generally speaking, it's going to be pretty quick. It's not like that many pushes of a button to plug some stuff in up here, and make sure you get something about like that. And if you get something different, then either you entered it into your calculator wrong, or one of the steps along this way was erroneous. Either way, it's just a mistake. Don't beat yourself up for it. But that's what checking your work for, right? Measure twice, cut once is the adage in the world of carpentry. And I guess it's like calculate twice and check in mathematics. Yeah, if I can calculate something 2 different ways and I get the same number 2 different ways, I'm like, it's probably that thing that I just calculated. Odds are I didn't do it wrong 2 different ways. So I think I'm going to call it good here and say thanks for watching. I appreciate your time, and I will catch you on the flip side. Bye.